The Markthal in Rotterdam epitomizes modern construction excellence, overcoming the city's unique soil challenges through innovative engineering techniques. The project began with a robust perimeter wall employing a combined wall system of steel pipe and AZ-type steel sheet piles to mitigate groundwater infiltration and ensure stability. A network of over 2,200 piles, initially functioning as tensile piles, anchored the structure, resisting buoyancy forces before transitioning to compression piles as floor slabs were completed. To manage groundwater pressure and ensure soil stability, the construction pit was filled with water to levels above NAP early in the process. Excavation continued underwater to depths of NAP minus 12.1 meters and locally to NAP minus 13.1 meters before the installation of an underwater concrete floor. This approach effectively balanced external pressures and enabled the seamless progression of the Markthal's construction. It was initially uncertain whether any leakage could be adequately controlled using open dewatering on the pit bottom. Therefore, as a control measure, the dewatering plan included the option for pressure relief dewatering to lower the groundwater pressure to the excavation level. A maximum lowering to NAP minus 6.0 meters was imposed to limit effects on the surroundings. Without well formation or leakage, the dry excavation required lowering the pressure head to about NAP minus 4.5 meters to maintain vertical stability of the cover layer. In the end, no visible leakage occurred during dry excavation, likely also due to the horizontal anchoring of the Holocene cover layer from NAP minus 12 meters by the new foundation piles. This targets the lowering of groundwater pressure from deeper, confined aquifers. Deep wells with submersible pumps are installed around or within the excavation site. To prevent uplift failure, also called heave, of the excavation bottom, especially before the construction of a heavy base slab. Implementation: multiple wells were drilled to depths of up to 30 meters, each capable of pumping 45 to 55 cubic meters per hour. Monitoring systems ensured groundwater levels remained within safe limits to protect sensitive nearby structures like the Lorenskirk. To determine the effects of pressure relief dewatering in Rotterdam, a numerical geohydrological model was set up using the finite element program MicroFEM. The model consists of 6 layers. The values for geohydrological parameters were taken from the groundwater map of the Netherlands and Regis, and then calibrated using long-term data from the Rotterdam Groundwater Monitoring Network. The combi wall mostly affected the groundwater flow in the top layer and the Holocene cover. In the Pleistocene aquifer, there was no significant influence because the sheet piles didn't extend into the sand layer. The water demand for the Markthal's pressure relief dewatering is heavily influenced by whether other dewatering operations are active in the center of Rotterdam. There was a large water inflow from the river, and it minimized the impact of dewatering on the Lorenskirk by maintaining higher groundwater levels around the building. However, this same inflow also posed a challenge, as it made it more difficult to achieve and maintain the required pressure head reduction within the construction pit. Since the timing of various dewatering projects could change, 3 scenarios were modeled for the permit application. The final dewatering system design consisted of 9 wells, mainly concentrated on the south side of the construction pit. To protect the historic Lorenskirk during the Markthal excavation in Rotterdam, engineers analyzed long-term groundwater data. They determined that lowering the pressure head in the first aquifer to NAP minus 5.5 meters for up to 6 months would not cause ground settlement. The contractor, Jadon, implemented a dewatering system with 9 wells around the construction pit, manually controlled. Groundwater levels were continuously monitored using pressure sensors in 8 perimeter observation wells and within the extraction wells gravel filters. All sensors and magnetic flow meters were connected to the Priva system, recording data every 30 minutes and providing real-time remote access. A deep observation well was also installed in the intermediate sandy layer, and the city operated a similar setup near the Lawrencekirk to monitor potential impacts. 7 wells operated regularly, with 2 on standby for emergencies, remotely activatable. Extracted groundwater was discharged through a pressurized pipeline beneath the Steigersgracht Canal to the Leuvehaven harbor. A booster station with pumps triggered by water levels in the sand trap and aeration tank maintained consistent flow. A T-connector at the pit's northwest corner allowed re-infiltration of water near the Lawrencekirk if needed. Monitoring showed slight upward ground movement over time, confirming geotechnical stability. In December 2011, a northwesterly storm raised new Maas River levels, increasing groundwater pressure and uplift risk. Real-time monitoring via Priva enabled prompt pump capacity adjustments, effectively managing the risk and ensuring excavation stability. A careful dewatering process was undertaken, methodically lowering the water level to maintain structural integrity while paving the way for further construction activities. As the foundational challenges were addressed, attention turned to realizing the Markthal's iconic arch through advanced engineering techniques. The iconic arch was realized using tunnel formwork, with temporary support towers aiding during construction. Completion of the arch's structural system relied on highly tensioned steel cables that prevented outward thrust. The construction of the curved roof and apex of the Markthal's arch was one of the most critical phases of the project, requiring advanced engineering techniques to ensure structural stability. As construction reached the 10th floor, both arch legs were temporarily capped until the keystone was installed to lock the arch. This process helped maintain resistance to lateral forces during construction. To improve efficiency and control, the curved roof was divided into 4 main sections. Each section was carefully managed to preserve structural integrity during the build. For each section, temporary supports were essential. 2 large temporary support towers were installed under the arch to stabilize the 2 segments of each floor during both the construction and curing phases. The arch was completed with the placement of a central keystone element at the apex. This keystone was critical in locking all 4 roof sections together, enabling effective load transfer from the roof to the vertical legs and eventually to the foundations. After installation, the arch became self-supporting, with loads channeled down the curved structure through compression. This eliminated the need for internal columns, allowing for a spacious, uninterrupted interior. However, the compression forces generated horizontal thrust at the base of the arch. To counteract these forces, tension anchors and integrated tensioning systems were installed beneath the structure. Additionally, the building's glass facades contributed structurally. Acting in tension, they helped stabilize horizontal forces and formed part of the building's closed structural loop. The Markthal's cable net facades are a defining feature, combining transparency with advanced structural performance. Each facade measures 34 meters high and 42 meters wide and consists of 22 horizontal and 26 vertical galvanized steel cables. The cables form a grid that divides the facade into glass panels measuring 1.5 by 1.5 meters. This configuration supports the structure while providing panoramic, unobstructed views. Each 31mm diameter cable was pre-stressed using a hydraulic tension bridge with a maximum applied pretension of 300 kilonewtons. During the process, the cables were stretched approximately 150 millimeters. To accommodate the long-term creep of the concrete, an extra reserve of 50 kilonewtons was built into each cable's capacity. The cables are anchored in steel boxes embedded into the concrete arches and foundation, ensuring long-term stability. One of the biggest challenges in implementing this transparent facade was managing the deflection of glass panels under wind loads. Unlike rigid mullion systems, cable net facades allow for significant movement. In Markthal's case, wind loads could cause the facades to deflect inward and outward by up to 700 millimeters, resulting in a total displacement amplitude of 1.4 meters at the center. To handle this movement, special detailing was required at the connection points between the cable net and the glass. The system used silicone joints between panels to allow flexibility while maintaining airtightness and waterproofing. These joints accommodated in-plane and shear movement from both wind and thermal expansion. At the panel corners, rubber profiles were used to absorb torsion and prevent stress from concentrating in the laminated, heat-strengthened glass. In frameless or minimally framed areas, butt-joint silicone sealants filled the gaps between the panels to maintain a smooth and continuous surface. This detail helped the facade remain functional and safe despite the dynamic nature of its support system. Overall, the Markthal's arch and cable net facades represent a balance of architectural vision and engineering precision, demonstrating how structural systems can enhance both function and form in complex urban projects. This week, we explored the Markthal project in Rotterdam, how precise dewatering and structural coordination can enable complex urban construction without compromising surrounding heritage or stability. The careful lowering of groundwater ensured excavation safety and preserved nearby sensitive structures. Once the site was stabilized, construction transitioned seamlessly into the iconic arch phase, where innovative engineering allowed for a column-free interior and visually striking cable net facades. The integration of flexible, weather-responsive materials and tensioned structural systems not only ensured durability and performance, but also emphasized openness and transparency. Next week, we'll shift focus to ventilation systems and underground heat storage, exploring how energy performance and indoor comfort are integrated into large-scale architectural projects.